Okay, in this example, they're giving us this function. Let me bring it down here for us. There we go. All right. And we want to take the derivative of it. All right, how do we do it? Well, a couple rules you want to keep straight. So we know, so first off, this isn't what's called an exponential function. What? Exponential. I can't spell and talk. Here we go. Exponential function. It's a T there. Meaning what? X is in power or W or whatever. You know, the letter, I should say, the letter is up there in the power zone. As opposed to, let me make sure we're clear. If you had something like, say, X or W, I'll go with W since they're using W, whatever. W to the fourth, what would be the derivative of that? Well, you know that, just bring down the four, subtract one from the power, boom, yeah. And that's just called a polynomial. So when the letter is in the base and there's just numbers in the power, that's just polynomial. You already know those rules. But now we're looking at examples where the letter itself is up in the power. The base is a number and the letter's up in power. Well, that's exponential. And see, exponent, right? Come from the idea of exponent, meaning the letter is in the exponent zone. The X or whatever the letter is, the letter is in the power zone. So what do we do? Well, they're a whole different category of derivatives. For e to the x, he's our favorite one. He does nothing. We always call him our favorite because he does nothing. Now, why does he do that? Because e is the perfect number. Remember, e is the special number, 2.718, whatever, whatever. Just like pi is a special number, 3.14159, blah, 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 blah. What's he about? He has to do with circles. I won't go into it. Want to talk to me in offstairs? I'd love to tell you how the ancient Egyptians first discovered pi by measuring circles and da 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 da. But we've just discovered it. It's part of the created order of how circles work. Well, in the same way, e to the x is a number we discovered, a special number, but he does a calculus thing. A few things. One of the first and main things we see that he does is he's the exact number to be our favorite derivative, meaning he does nothing. He's like a mere reflection. He's the mere reflection derivative. He does nothing. Okay, why am I going on and on about e? This isn't e. Right. Well, because if you have any other number, say like 9 to the x, that's almost the same kind of thing. That's still exponential because, right, because the x is in the power zone, the numbers in the base. So when the letters in the power zone, we call that exponential. Letters an exponent zone, we call it exponential. The derivative, it's almost like you should think it's like e to the x, meaning it's like e to the x. It does a mere reflection, but because it's not the perfect number e, it's 9 or it's some other number that's not e, 2.718, blah, 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 the special number, it's got to have an adjustment. And the adjustment is the natural log of that base. Let's call that the adjustment. And so that's the derivative rule. So we go, oh, okay, okay. Then come on down here. The derivative is going to be, at first, he does nothing, times now the adjustment, which will be natural log of 9. Because why? Because that was not the perfect number. So I'm going to do this in pieces. So this is the mere like e to the x. This is the adjustment because it wasn't the perfect number because it's not e, it's 9. It's not the perfect number. I don't know if you know, e is the perfect number. Well, it's the perfect number for derivatives. Anyway, but that's not all. You might think, well, so we're done. That's it. Well, remember what rule, you probably know, what rule is always there? He's always there. No matter what other derivative rule you're using, he's always there, the chain rule, right? If you're doing any other rule and the inside of the function where the plug-in spot is, the holes in the toaster, is anything other than a simple X or W, whatever your letter is, then the chain rule says, hey, don't forget about me. I'm always there. Chain rule says you got to go times the derivative. So I was sure to that. It's easy. 1, bring it down, -8, subtract 1 from the power, that goes away. 7 is 0. You can go -8 plus 0 if you want, but who cares? It's just -8. And you can just Yeah, oh yeah, that's it. I was going to say something else, but it would be wrong. That's it. We can put the -8 in the front if you want. You know what you might think? This is what I was going to say. You take the -8 and multiply by the 9, but I'm wrong. You can't. Why? Because that 9 has stuff in his power zone the -8 does not. So you can't put them together. You can put the -8 in the front if you want. You don't have to. You can leave it at the back. It's got to be times though, right? Those parentheses make it multiplied. If I was to write, let me help with that. If I was to write -8 like that, that would mean subtract 8, wouldn't it? You got to put parentheses around it. Then it means multiplied by -8. So we have to do that. That's why a lot of times it's better just to put it in the front. That way you don't need parentheses. It means -8 automatically. No, it's not subtraction now. Why? Because now it's not between two things. So if you just write, you know, if you left off those parentheses like that, now it means subtraction. Why? Because it's between two things and there's no parentheses. That means subtraction. But parentheses, okay, now it's multiply. So anyway, that's why we like to put it in the front. You don't have to, but it's just no chance for a mistake. If you stick it in the front, that's kind of good form, um, like that. That's probably the cleanest way. That's why they wrote the answer that way. Well, actually, they put the LN9 in front too. Whatever. It doesn't matter. So there we go.